This is the first section of the modern physics topic. This section is called the wave-particle duality of light. In this section, I'll be explaining how light can act as both a wave and as a particle. Back in the 1800s, the late 1800s, scientists were arguing over whether light was more like a wave or more like a particle. At that time, they hadn't done enough experiments yet to determine whether light was a wave or light was a particle. We know that a wave of light looks like this. And we might draw a particle of light like this. So this is a wave, and this is a particle. These are models. They're pictures that we use to help us understand how light behaves. But again, early on, around 1900 or so, the scientists had not yet done enough experiments to decide whether light should be drawn in the textbooks like this or like this. Now, let's talk a little bit about some of the proof of light's wave nature and some of the proof of light's particle nature. Well, we know that light waves have a frequency and a wavelength. Because a light wave has a frequency and a wavelength. Now, for this wave, the wavelength is right here, right, crest to crest. For this wave, I'll make a longer wavelength. All right? So here's the wavelength for this wave. So now, this wave has a shorter wavelength and a higher frequency. This wave has a longer wavelength and a lower frequency. Because light waves have frequency and wavelength, we can think of them as waves. So, frequency and wavelength prove the wave nature of light. Now, what about the particle nature of light? Well, for example, when a light wave strikes an electron, now I'll draw it with a high frequency, like for example an X-ray. When the light wave strikes the particle, it imparts some energy and some momentum to the particle. Just as if two pool balls were to hit each other on a pool table. Now, what will happen in this case is that the electron that was stationary will move off, possibly in this direction. So the electron acquires some momentum because it's moving now, and some kinetic energy from the light wave. And the light wave will reflect or rebound off the electron with a longer wavelength. Now, perhaps you know that a longer wavelength implies a lower frequency and therefore lower energy. So the light wave struck the electron, transferred some of its energy to the electron, and now the light wave has less energy and therefore a lower frequency and a longer wavelength. This is light acting more like a particle, like pool balls hitting each other on a pool table. So this demonstration proves the particle nature of light. Now, there are other demonstrations. Originally, they were done as experiments, but we can simply discuss them as demonstrations to prove light's wave nature versus light's particle nature. Light can be reflected. We know that a light wave I'll draw it simply as a plain arrow. We know that a light wave can reflect off a surface. But what about a particle? Like, for example, a ball, a regular ball, or a marble. If you throw the ball down at the ground, it will reflect off the ground. So you see, reflection does not prove whether light is a wave or light is a particle. We'll draw the wave here, reflecting off the surface. You see, waves can be reflected, but particles can also be reflected. So reflection is not a phenomenon that will help us to decide whether light is more like a wave or more like a particle, because both waves and particles can be reflected. So reflection does not help our discussion today. Let's look at some phenomena in which light behaves more like a wave or more like a particle. Let's look first at diffraction. Diffraction. The passing of a light wave through a small slit or around an obstacle. We'll look at an example of double slit diffraction. Because after the light waves are diffracted through both slits, we want to see the interference on the other side. But let's draw double slit diffraction first. Here's one slit, a slit or an opening. This could be a piece of wood or a piece of metal, any kind of barrier. And here's my second slit. So this is a double slit. Now, I'll have the light waves come from this side. I'm drawing only the wave fronts or the crests. So if these waves were coming at you, you would see crest, 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 crest. So the waves are traveling in this direction. They're going to pass through the opening and then start all over again on the other side. So let's do that. I'm going from here, I'm going to make a crest, and then I'm going to show you the trough also. A crest and a trough. A crest and a trough. Couple more, a crest and a trough. All right, that'll do it. Now, over here, the same thing happens. We have a crest and a trough and a crest and a trough and a crest and a trough. You see, I'm trying to make them even so that the diagram is somewhat symmetrical. Now, this diffraction occurs because light can travel as a wave. Pure particles are not going to do this. Now, on this side, because we have two sets of wave fronts, they're going to interfere with each other. Let's see how the interference occurs, what kind of interference occurs, and why. Now, here, for example, we have a solid line, which represents a crest, and another solid line, meeting. Since this is crest to crest, this is an example of constructive interference. Here, for example, we have a dotted line, which represents a trough, and another dotted line, which represents a trough. We have two troughs. Again, an example of constructive interference. Crest to crest or trough to trough results in constructive interference. Crest and crest are both going up. They work together. The resultant is a larger amplitude. Trough and trough are both going down. They work together. The resultant is a larger amplitude. Now, what about here? Here we have a crest and a trough meeting. That would be an example of destructive interference. So you see that double slit diffraction results in interference. And this would not occur. The diffraction would not occur. The interference cannot occur unless we are talking about a phenomenon which acts as a wave. So, one of the things I'd like you to write down in your notes is that diffraction and interference prove the wave nature of light. Diffraction and interference prove the wave nature of light. And you can see, you can have diffraction and interference on the same diagram. Diffraction and interference prove the wave nature of light. All right? Now, what about the particle nature of light? Can we do a demonstration of an experiment that was done back in the early 1900s to prove the particle nature of light? Now, what experiment would that be? Well, a man whose name I'm sure you've heard, Einstein, demonstrated something called the photoelectric effect back in the early 1900s. The photoelectric effect. As a matter of fact, Einstein received a Nobel Prize for his explanation of the photoelectric effect. Let's see, in a very basic way, how the photoelectric effect works. I think we all know that the frequency of light determines the color of the light, at least for visible light. We know that X-rays and gamma rays and ultraviolet don't have a color that we can see. But visible light, for example, high frequency purple light, right, violet light, has a very high frequency. It has a high frequency. It has a very short wavelength. So this is what it would look like as a wave. And because it has a high frequency, it is high energy light. Now, next in line would be indigo, but I don't have an indigo whiteboard marker, so we'll just have to deal with blue. I'll make indigo a mixture of purple and blue. So here's our indigo, and then blue, and then green, and then yellow. I don't know if you can see the yellow. There's yellow. I think all you can really see is the cap from the marker. Trust me, it's yellow. Now, here's orange light, all right, and red light. All right, now the red light is low frequency. If I were to draw a picture of the red light wave, it would look something like that. And low frequency would mean low energy. Now, I know you recognize Roy G. Biv. The reason that I drew it backwards is because on your reference table, the electromagnetic spectrum, New York State put the high frequency light on the left side of your reference table and the low frequency light on the right side of your reference table. So I did it the same way as your electromagnetic spectrum reference table. But you can recognize Roy G. Biv backwards. Okay? So, we know that violet light has the highest energy and red light has the lowest energy. Now let's see what happens when we shine red light and violet light onto a piece of metal, and all the other colors as well. And again, what we're doing here is demonstrating the photoelectric effect. And we're going to see that the photoelectric effect will prove the particle nature of light. Let's draw a piece of metal. All right, this is a piece of metal. And let's shine red light onto that piece of metal. Except, I'm going to draw the light as little photons instead of as waves. So these are photons, little particles of light. Now, in the metal, of course, there are electrons. And for this particular type of metal, the red light does not cause these electrons to be ejected. The electrons don't get energy from the photons. They stay put. They don't get enough energy to be ejected, to be shot out. All right? So what we do is we try a higher energy photon. Let's try, for example, orange. Are the orange photons strong enough to eject the electrons from the metal? Let's see. All right, the orange photons, we shine orange light. Orange light has a little more energy than red light. And the orange photons hit the electrons, but the electrons don't shoot out yet. The orange photons are not strong enough. They don't have enough energy. What about yellow photons? Here they come. I don't know if you can see them. I know you can see the marker. Here are the yellow photons. Here they come. They have more energy than the orange ones or the red ones, but they still don't have enough energy. They don't have enough frequency. They don't have enough energy. Let's try a higher frequency light. Let's try green. And let's see if any of the electrons shoot out. All right, so let me extend my piece of metal. I need a bigger piece of metal. Here we go. All right, and here are the electrons. And what happens when a green photon hits an electron? Wow, did you see that? When the green photon hit the electron shot out of the metal. Watch again. When this green photon hits an electron, maybe he'll hit this one. This green photon hits the electron and boop! Wow. I guess the green light is strong enough to cause electrons to be ejected from the metal. So that means that green light is the minimum energy, the minimum frequency, the lowest possible, the threshold frequency that will allow electrons to be ejected from the metal. These were not strong enough. Now that also means that blue light, which has a higher energy still, will also work, and of course indigo, and of course violet. All of these photons are stronger than the green. The green works, so these will also work. They will also cause electrons to be ejected from the metal as they hit the electrons. Pew, 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 pew. There they go. Now, a simplistic explanation for why this proves the particle nature of light would be something like this. If light were only acting like a wave, then this wave would keep coming and coming and coming, and sooner or later the electron would be ejected, even by the red light. But that's not what happens. No matter how long we shine the red light on the metal, the electrons are not ejected. So that proves that light comes down in a discrete little particle called a photon, and that's it. It's over. The photon hits. If he has enough energy, the electron is ejected. If he doesn't have enough energy, it's done. And his buddies, who are all identical to him, will not have enough energy. The energy doesn't build up. It's a particle. It hits, and it either works or it doesn't work. It's done. The photoelectric effect proves that light has a particle nature to it. Light sometimes behaves as a particle. Now, I also want to mention that this phenomena is the basis for solar cells. Light hits a piece of metal or a metalloid, semi-metal, and electrons are ejected. These electrons can be made to flow through wires. So this phenomena is the basis for solar cells and the solar energy industry. All right, so just to summarize what we've talked about here today. Light can be thought of as both a wave and as a particle. To prove the wave nature of light, we look at such experiments that show that light has a frequency and a wavelength. We look at diffraction and interference. These words go along with the demonstrations and experiments that prove the wave nature of light. When we draw light like a wave. Now, what about proving the particle nature of light? How can we prove the particle nature of light? Light, little particles of light, little photons, have momentum. We know that momentum for large particles, like a baseball, would be the mass times the velocity. So certainly the fact that light has momentum, which can be transferred to another particle, like an electron, proves the particle nature of light. I do want you to keep in mind that photons have no mass. Even though they have momentum, they have no mass. I know that's a little strange, but we're just going to leave it as it is for now. Photons have no mass, but they do have momentum, which can be transferred to another particle, like an electron. This proves the particle nature of light. And finally, the photoelectric effect, for which Einstein received the Nobel Prize back in the early 1900s. The photoelectric effect also proves the particle nature of light. So I hope you understand now that light is sometimes thought of as a wave, and light is sometimes thought of as a particle. This is called the wave-particle duality of light. In some demonstrations and experiments, light behaves as a wave. And in other demonstrations and experiments, light behaves as a particle. I'll see you in the next section.